Hi guys, welcome to Material Science lecture. This is lesson 3 for module 4, in which we will continue our discussion from yesterday, where we talk about deformation, plastic deformation, in which plastic deformation is the basis of all forming process. So in order for us to form the materials to its final shape, we need to apply forces, external forces that are huge enough in order for the yield stress of the materials to be exceeded, and plastic deformation will start to happen. So during this process, microstructure of the materials will change. So as I think we've talked about it so several times already, microstructure is one of the most important factors affecting the chemical and physical properties of metals. So by knowing the microstructure, we can predict the behavior of the materials. So they are also important in predicting the failure of the component in certain conditions. So we must know what happened during this plastic deformation that will change the structure of the materials. And can we do something when this structure is changed? So we want to know what can we do in order for us to manipulate the microstructure of the materials. So there are processes that the materials, when they've already been solidified and we shape them, there are processes that we call as heat treatment. Specifically for this lesson, we will look into a heat treatment called process annealing. So during this process annealing heat treatment, there are phases that the microstructure will undergo in order for it to change its shape. So we will look into this process, these 3 phases, which is the recovery, recrystallization, and grain growth in this lesson. What happened during this process? So the learning outcome for this lesson is for you to be able to describe recovery mechanism during process annealing, for you to be able to describe what happened during recrystallization in terms of both alteration of the microstructure and also the mechanical characteristic of the materials, and also to describe the phenomenon of grain growth from both macroscopic and the atomic perspective. As I have mentioned earlier, a forming process or forming operations such as rolling, forging, extrusion of a metal is a process in which we shape the materials, we change the shape of the materials of a metal component through plastic deformation. So during this process, plastic deformation induced by cold working operation. So cold working operations such as rolling, forging, extrusion, and drawing is very common to shape a materials such as metal into its final product. And there are consequences to the microstructure when we form this process. So some of these consequences of plastically deforming a polycrystalline metal is that the property will change. And some of these properties is the change in microstructure. The size or the shape of the grain will start to change during this cold working process. And also we will induce strain hardening. So the materials that we perform this forming process will have a higher strength when we introduce plastic deformation. So for example, that I gave you yesterday, this wire here, this metal strip of aluminum, this is almost 100% aluminum, pure aluminum. So when I introduce plastic deformation, so I change its shape the first time on that particular location. And if second time I induce plastic deformation again, so what's going to happen is actually I need a stronger force for me to change them. And then the third time, a little bit stronger force is needed to bend it. And if I try it again, it's actually every time it's going to go, it's going to get stronger and stronger. But eventually, they will start to break. So at the same time, we increase the strength of this material through strain hardening by performing the plastic deformation over and over again. We increase the strength, but at the same time, we reduce the ductility. So that's what happened during plastic deformation or forming process. So if you imagine you have a foil of aluminum that you go through rolling process to make them thinner and thinner. Every single time that they go through this rolling process from one roller to make it thinner to another roller, you induce strain hardening. You make this foil stronger and stronger by the introduction of more and more line defect or dislocation. So this dislocation will start to entangle with each other, and there will and your materials is going to be stronger due to this entanglement of this dislocation. But at the same time, because of that, the ductility of the metal will reduce. So by the increment of dislocation density, this also can happen during this process of plastic deformation. Also, the electrical properties can change, and also the corrosion resistance of the materials can also change after we form the materials. So we want to know, can we change this microstructure, or can we change these properties after we induce plastic deformation? Because some of this change is not good for the materials. So we want to know, can we change it back to the pre-coal or pre-forming microstructure, in which the microstructure have different properties. So this is what we will learn from this lesson. So a heat treatment process that we call as process annealing can be performed to revert the properties back to its pre-plastic deformation. So why we want to return it back to its pre-plastic deformation is because one example is because we want it to be more ductile. We don't want materials that is brittle if we are going to use them in a lot of mechanical engineering application. If we want to use it as a structural application, we don't want them to be brittle. We want them to be ductile, and it's much safer if the materials is ductile. So we want to change some properties back to its original condition. So heat treatment, process annealing is one way of doing it. During this heat treatment process, there are 3 phases that involve that can change the microstructure. And these phases of process that happen is what we call as recrystallization, recovery, and it can also be followed by grain growth. But before we go and have a look at what happened during this heat treatment process, let's have a look at this few animation that I have here explaining what happened during forming process. So I have here an animation of rolling process. So during this process consists of passing metal between 2 rollers, which exert compressive stresses and reducing the metal thickness. So as you can see here, the metal passed through a roller over and over again to change its dimension and to change its, some of them to change its shape as well, in accordance to the shape of this roller. So what's going to happen during this process is that the metal, the grain shape of the metal, if we look under the microscope, from when it starts to when it's finished, it's going to be looking different. So, and this change is not necessarily going to be a good change. So we want to be able to change it back. So this is what happened during rolling process. And for forging, forging is another step of plastic deformations to change the shape of the material. So as you can see here, this component is made from a semi-finished product, which is a strip of metal, and then it's being forged, which involve a single piece of metal deformed mechanically by application of successive blow or by continuous squeezing to its final product. Again, what's going to happen after this process is that the grain shape will change. Extrusion is another type of forming process in which, as you can see in this process here, in this animation, a bar of metal is being forced from an enclosed cavity via a die by a compressive force applied by a ram. So the final product will follow the shape of that die. So during this process, again, the grain shape of the materials will change. So lastly, I have another example of forming process of a metal in which wire or any piece of metal is being drawn. So drawing is, instead of being forced by compressive force, it is being pulled through a die by means of tensile force applied to the exit side of the metal. So all of this process, the rolling, extrusion, drawing, and also forging, will cause the shape of the grain to change. So this process of cold working, of rolling, extrusion, and so on, will induce strain hardening. So what happened during this cold working or strain hardening process? So if we look at the microstructure, each of the grain of the materials will become deformed. So they will be elongated in one direction and contract in one direction. So as you can see here, as this schematic, this metal, when it undergo rolling process, each grain of this metal will become elongated in the direction of that rolling, rolling process, and it will be contracted in one direction, in another direction, in the lateral directions. So this change will change the cross-sectional area of each of the grain. The materials will will have an increment in strength, but the ductility will decrease. So this is what happened to each of the grain during this cold working process. So one example of engineering application that I can give you for a forming process to make a final product is involving copper alloy. So copper alloy has been used extensively in marine application. They've been used in a lot of other applications as well, but they are extensively used in marine application because they have a very good corrosion resistance. So they did not react with seawater. So a lot of offshore components are made of copper alloy as well. So as you can see here, I have two products here, final component of nuts and bolts and fastener, and also the hull, the cladding for this hull of the boat is made of copper alloy as well. So they come from so this is another product, a few products of copper alloy. They come from a semi-finished product that has gone through this forming process. So as you can see in this image here, there's a roll of copper foil, copper alloy foil, and also, as you can see here, bars of copper alloy that has been extruded, gone through extrusion process. And if we look at the microstructure of these products, what we can see is that the microstructure that is plastically deformed. So it has a grain that has been elongated like this. So you can see that the elongation of this is according to the direction of the rolling process. So this is a microstructure that has been of an alloy, of copper alloy, that has gone through the rolling process. So this microstructure is anisotropic. So what is anisotropic? I have explained in class a few times. An isotropic is when you have a microstructure that is very directional. So when you test them from different direction, it will give you different properties. So for a lot of mechanical engineering application, we want to avoid this. So I think I need to explain a little bit more about anisotropic materials. So anisotropic materials or anisotropic microstructure is direction dependent. So it is made of unsymmetrical crystalline structure, and also the mechanical properties due to this anisotropic behavior depends on the orientation of the material's body. Each surface will react differently when we apply the same load at different axes. So this implies that if a certain mechanical or thermal properties is measured along x-axis, the measurement will be different if we take it from y or z axis. So that's what anisotropic microstructure means, anisotropic behavior means. So I think you can deduce by that statement is that we want to avoid this if it's a structural application, because we don't know where the accidental load is going to come from. If we are certain that, for instance, these materials, if we're certain that we are just going to apply the materials in the direction where of x-axis for example, if we're just going to apply the external force on the x-axis, it will be safe. But what if I have accidental load on the y-axis with the magnitude of the force that is high enough, that is okay in the x direction, but in the y direction, it is not okay. So we want to avoid this. So that's why we want to avoid anisotropic materials for a lot of mechanical engineering applications. So not only the microstructure change from isotropic to become anisotropic, what's going to happen as well during cold working process is that the mechanical behavior of the materials, such as its yield strength, its tensile strength, and also ductility will also change. So I have this exercise here. This analysis of cold working of a copper rod here. So I have done an extrusion process, for example, or rolling process in which I change the dimension, the diameter of these materials from being a larger diameter rod to become a smaller diameter rod. So I've conducted a rolling process or drawing process in which it changed its dimension. So I can calculate how much percentage of co-working I have induced to this rod by using this equation here, in which I calculate the change of cross-sectional area divided by its original cross-sectional area times 100, I figure out that the co-working percentage is 35.6%. And when we do tensile tests, what we discover is that the tensile properties of these materials, such as yield strength and tensile strength, has changed. Its ductility also changed. So if we plot the graph of co-working percentage against the mechanical properties of the materials, we figure out by doing this 35.6% co-working to this rod, what's happening is that the yield strength of these materials increase. So from around 150 megapascal, it is increased to 300 megapascal. And also its tensile strength also increased to 340 megapascal. So you can see that by doing whole working process, it induces strain hardening. The materials become stronger. But when we do the calculation for the ductility has changed. So for this example, it is a copper metal. So copper metal, in its pre-core working, before it's being core work, it's very ductile materials because of its crystal structure. It has FCC crystal structure. It has a huge number of slip plane where when we activated plastic deformation, the dislocation will slip over this huge number of slip systems. So they are very ductile materials. But as we induce plastic deformation, it will reduce its ductility. So this is the mechanical properties that's going to change when we induce plastic deformation. So let's say if now I have already done this 12.2 millimeter rod diameter and I want to reduce it again to 10 millimeter. So I can calculate that core working percentage again, and we can see what's going to happen to the mechanical behavior of these materials. So obviously from its original dimension to the next previous one, the core working percentage is going to increase. So you can see that there will be an increment in yield strength and tensile strength, but the ductility will keep reducing. So those are the things that's going to change when plastic deformation is performed to the materials, when we perform forming process. So as I have mentioned earlier, we can change this back to its pre-core working or pre-forming process microstructure by a heat treatment process we call as process annealing. So what happened during this process annealing is that the microstructure, the elongated microstructure, will be changed to equix microstructure. So equix microstructure is a microstructure that have a dimension that are equal in each of its direction. So there, we want to change it from this elongated, which is anisotropic, back to equix microstructure. So what we need to do is actually to perform heat treatment process in which this room temperature metal will be heated up to a higher temperature. So the temperature is below the melting temperature. So you cannot heat it up so that it will melt. You don't want that. You just want to heat it up below the melting temperature. So approximately at 0.4, it's melting temperature. So during this process of the heating up process from room temperature to the 0.4 melting temperature, the dislocation will start to move. So diffusions of atoms starts to happen during this process. So when we study diffusion, we know that the diffusions will be activated at higher temperature. So atoms will start to move. Dislocation will start to rearrange. So they will be more mobile at this point. And after that, that's the process that we call as recovery process. So the dislocation is rearranging themselves. And after that, we will need to hold it to that temperature for a certain period of time in which new nuclei or nucleus or seed will start to form at this position. So this position where dislocation arranging themselves. And as we've learned from solidification, as the new seed is formed, atoms will start to latch themselves, other atoms will start to latch themselves in that on that nucleus. So this can happen because we have increased the temperature. Atoms is mobile, they can start to diffuse, and they will arrange themselves to these new seeds that is formed in various locations of the grain. And this process is what we call as recrystallization. And if we let them to sit for a long time in that higher temperature, atoms will keep diffusing and diffusing. The grain is going to grow bigger. So depending on the rate of cooling, we can stop them from grow bigger or we can let them to grow bigger. So bigger microstructure means that the materials will be more ductile. smaller microstructure means that the materials will be having higher strength. So that depends on what we want. So if we want it to be to stop at a very small microstructure, we can fasten the cooling rate. So that's what it is. There are three processes that's going to be involved in this process annealing, which is recovery, recrystallization, and also grain growth. So during the recovery process, the deformed grains will reduce the stored energy by the removal or the rearrangement of defects in the crystal structure. So as we learned yesterday, dislocation, they interact with each other. So if we have two dislocations that have the different configuration, because now we heat up the materials, the temperature is higher, they can move. So when we have different configuration, they will create a perfect plane when they starts to interact. So there will be a removal of dislocation during this process. And because they are mobile, they can also rearrange themselves. So this is what happened during recovery. So this will result in the result in the enhanced atomic diffusion at elevated temperature. I will visualize this recovery process using this 1 grain of microstructure. So imagine I have this 1 grain, just 1 grain, okay? And I have this just a shape of square here representing 1 grain of a microstructure that has been elongated. And during plastic deformation, as I said, there will be a lot of dislocation will be introduced during this process, this forming process. So the deformed structure will have a huge number of dislocation introduced during this process. And because we heat it up, the dislocation will start to be mobile. So there will be a cancellation of dislocation at a higher temperature. Those that have opposite configuration, we have edge dislocation with half plane here, and we have half plane here. When they start to be able to move, they will meet each other and cancel out. They will produce a perfect plane. So that will cancel, all right? So at higher temperature, dislocation will become mobile. They can glide and climb, and if two opposite dislocation meet, they will cancel out. This will leave only dislocation with the same configuration in the grain. So the remaining dislocation with the same configuration, because it's high temperature, they also are mobile. So the remaining dislocation will align themselves into ordered array where their individual contribution to the stored energy is reduced by overlapping their strength field. So if you look at this 1 grain itself, what you will see is that this arrangement of different configuration of dislocation. And there will look like a boundary, but it's a very low angle boundary. And this low angle boundary is what we call a still boundary. Beware that this is not a grain boundary. It still happens inside that 1 grain, but the dislocation arranging themselves, and it will look like they're creating a boundary that we call a still boundary. It's still inside the same grain, but they arrange themselves in ordered arrangement. So I have this animation here to show what happened during recovery process. When we heat them up from room temperature to the temperature where it's supposed to starts to recrystallize. So that period is recovery process. So this is an example of a microstructure that has undergone recovery process. So I have before this image here is before it's being heat up. So maybe I should write it down as before. So this is before, and this is after recovery. Not recrystallization yet, it's after recovery. When we start heating it up from room temperature, So in this region, before recrystallization starts. So as you can see here, the before image has a lot of dislocation. So you can see a lot of dislocation inside the grain. So if we just focus here, this is one grain, and we have a different grain as well. So just focus your attention to the one with the label as A. So before recovery, there are a huge number of dislocation. And after recovery, it starts to rearrange itself and creating, as what we can see here, a low angle boundary inside that grain. And the other one, the one with label as B, you can also see that the second grain has also this tilt boundary. So this is when the dislocation starts to move. If they have different configuration, they cancel out. If they have the same configuration, they will rearrange themselves. So you can imagine that if I visualize them schematically like this is subgrain 1 and this is subgrain 2. The subgrain 1 and subgrain 2 is being divided by this rearrangement of the dislocation. So this is a tilt boundary. So this is what happened during recovery process. And after this recovery process, when we get to a temperature that we want for annealing, and if we hold it for a certain period of time, recrystallization process will begin. So in this process, there will be a formation of new set of strain-free and equix grain. So the grains that will be formed during this by the end of this recrystallization process will have approximately equal dimension in all directions. And the grain will also have low dislocation density, and it is the same shape as the grain shape will be the same as the one before we conduct plastic deformation or forming process. So you might be wondering why we shape the materials at room temperature, at cold temperature, by performing this plastic deformation, inducing this plastic deformation at cold temperature. Whereas we know that materials become ductile at a higher temperature, why don't we shape them at a higher temperature? So there are processes that we shape the materials at a higher temperature, and we call them as hot working. So during hot working, the metal sample becomes soft and ductile. But at this process, we cannot observe the strain hardening effect. So the increase in strength and hardness will not be observed if we process or if we shape them at a higher temperature. So with cold working product, materials will become harder and also will have higher strength, and therefore, at the same time, we know the ductility will be reduced. So what we can do, we do co-working to increase its hardness and strength, and at the same time, we reheat them or perform heat treatment process in order for them to restore some of the ductility. So we get to shape them, and we get to increase its mechanical properties as well through co-working. And after co-working, we heat treat them and we can restore some of their ductility. So after the recovery process finish, so this is the recovery. So during this recovery process, the dislocations will start to move. The one without the same configuration will cancel each other. The one with the same configuration will start to arrange themselves to form tilt boundary. So this tilt boundary will be inside the original grain. So if you look at the grain will still have the same deformed structure from when the forming process being done. So if it's elongated, it will still be elongated, but there will be rearrangement of dislocation. So if you look at each of the grain, there will be a tilt boundary. So this tilt boundary, as well as the grain boundary, will be the region where atoms will start to diffuse. So atoms will start, because at this point, all of these atoms are activated. They are mobile. They can move around inside their crystal structure. If there's vacancy, they can move around. So what's going to happen is that at that tilt boundary, there's vacancy. Then also there are also at the tilt and the grain boundary, there's vacancy. They will go and around this region. And when they meet other atoms as well, and a lot more atoms at the same time, what's going to happen? They're going to form a bond. So the bond will create the seed. So the first seed, which is the nuclear will start to be formed at all of these regions of tilt boundary and also at the grain boundaries. And when we start having nuclear, when we learn about solidification, what's going to happen? If they're stable enough, they will start to grow bigger and bigger. So that's what's going to happen. At a higher temperature, the atoms will start to diffuse at the grain boundary and then at the tilt boundary. And when they meet other atoms, they will start to bond and they will create the nuclear. And the nuclear, when it's stable enough, they will grow bigger. And the new grain will form and grow until they completely consume the parent grain. And if we leave them, so this is the process, that's the process of recrystallization. So now we have this microstructure, which is equivox. It has almost the same, approximately the same dimension in all directions. So these materials is now going to be isotropic. So when initially they're anisotropic, after this recrystallization process, it is becoming isotropic. And recrystallization process needs time. Diffusion needs to happen over time. So depending on how long you leave them like that, at higher temperature, diffusions will keep going. Okay, so depending on your cooling rate, we can make the size of the grain grow bigger, or if we cool them rapidly, it will stay at that size. So depending on what we want to do next, we can make the microstructure, the grains grow bigger, or if we want to have the good strength and tensile strength and yield strength, we can cool them rapidly. So this is an optical microscope image of a brass alloy, which is a copper alloy that has gone through 33% cold working. So the dimension has been changed through cold working process. And as you can see, this first image here, the first image here is after recovery process, So we have, if I draw the cooling curve, so this is time, this is temperature. It has gone through recovery process from room temperature to 580 degrees Celsius. And as you can see, after recovery at this point, there are a lot of tilt angle inside this grain. So there's you can see the grain boundary and you can see the tilt angle, the low angle boundary inside this grain. And as the temperature remained at 580 degrees Celsius for 3 seconds, after 3 seconds, you can see that at the tilt boundary, from this image here, it's very obvious. You can see there's a small seed or small nucleus starts to form at that tilt boundary. You can also observe them at the grain boundary, but you can observe them everywhere. And if we stay at that temperature for 4 seconds, add another 1 second, you can see that there's a lot of this nucleus that starts to grow bigger and bigger. but we can still see the remnant of that original grain after co-working. So the new grain boundary, the new grains has not consumed the whole parent materials at this point. But after 8 seconds, if you hold it for after 8 seconds, you can see that the whole parent microstructure has been consumed with the new grain. So the grain size is now really small. The nuclear is it comes from the nuclear that nucleated at that tilt angle. So what's going to happen if we keep them at this temperature? So here in this image here, after 15 minutes, holding it at 580 degrees Celsius, we can see that the grain size is growing bigger, because atoms will also diffuse from one grain to another grain, so they are going to grow bigger. So after 15 minutes, you can see the grains grow bigger. But what if I use annealing temperature at a higher annealing temperature? So for instance, this image here is the same copper alloy, but instead of recovery temperature of 580 degrees Celsius, I use 700 degrees Celsius. After just 1 minute, you can see that the grain is growing bigger and bigger. This is because atoms will start to diffuse from one grain to another grain. It's still at higher temperature than the other one. We allow them to diffuse at a much faster rate. So by looking at that difference between when we anneal materials at different temperature, the grain size will be different at a different time. If we anneal them at a higher rate, higher temperature, the grain will grow. The grain growth is at much faster rate. So of course, the mechanical behavior will be different at a different annealing temperature. So here there's a plot of the influence of annealing temperature for 1 hour on the tensile strength and ductility of brass alloy. So you can observe here, if it's being annealed for 1 hour for 200 degrees Celsius, or you use 300 degrees Celsius annealing temperature or 500 degrees Celsius temperature, you can see that there will be a difference in terms of their mechanical properties. So this is what this graph is all about. So if we look at the 450 degrees Celsius annealing temperature, if we hold them for 1 hour, after we cool them, after it goes back to room temperature, and we test them, and we figure out that the tensile strength is at this point and the ductility is at this point. But instead, if we have annealing temperature of 300 degrees Celsius, once they are at room temperature, we test them. We test them with tensile strength. We figure out that the tensile strength will be different than the one at the 450 degrees Celsius, and also the ductility will be different. So their temperature also going to annealing temperature is also going to influence the mechanical behavior of the materials. So after the recrystallization process, if a specimen is left at a higher temperature beyond the time needed for complete recrystallization, the grain will begin to grow in size. So because diffusions of atoms will keep going. So after the recrystallization process finish, we have the time, we have already recrystallized all of the grain. If we leave them at a higher temperature, the grain is going to grow bigger and bigger. So for example, here I have two grains adjacent to one another, and they're already being recrystallized. This is the recrystallized grain. If we leave them at a higher temperature, the grain boundary will be shifted. So how is the grain boundary shifted? It's simply by atoms move from one grain to another grain. So as you can see from this illustration here, what's going to happen if we leave them at higher temperature, the atoms from grain 1 will migrate to grain 2, and the grain boundary will be shifted. So grain boundary motion is just the short range diffusions of atoms from one side of the boundary to the other side. So through this annealing process, we actually will make the materials change from anisotropic after it is being deformed plastically to isotropic microstructure. So if we look back at our copper metal, the example I gave you earlier on this lecture, after the recrystallization process, recovery recrystallization and grain growth, you can see that the microstructure is going to change. So the grain will going to change, the grain dimension. So from the first one after it's being cold rolled, this microstructure is very directional. So it's elongated in this direction, but it's become shorter in this direction. And as the material is being heat treated, eventually you can see that the size and the grain shape change to echoic shape. So the dimension of this shape are almost approximately the same in each of the directions. So they become isotropic microstructure. So isotropic microstructure have identical material properties in all directions at every given point. So it means that when a specific load is applied at any point in the X, Y, or Z direction, in isotropic microstructure, it will exhibit the same strength, the same stress, strain, and also Young's modulus, and also the hardness. So we want this microstructure mostly in structural application. So in summary, in this lesson, we've learned about co-working, how by performing co-working, it increased the hardness and strength, but it reduced the ductility, means that the materials become brittle, and this will prevent it from being further shaped since they can be easily fractured. Also, brittle materials is not good for load carrying application. So through process annealing or heat treatment process, plastic deformed materials can be returned back, the microstructure can be returned back to its pre-cold work microstructure. And this process of restoring this microstructure is called as process annealing, which involve recovery, recrystallization, and grain growth process. So that's about it for this lesson. Thanks for listening. I'll see you in the next lesson. Thank you very much.